Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Routers serve as the gatekeepers of network traffic, using IP addresses to determine how data moves between different networks. Their primary job is to read destination IP addresses, consult routing tables, and forward packets toward their next destination. Routers enable internet communication by separating broadcast domains and providing logical boundaries between subnets. This functionality makes them essential for structuring scalable and segmented network environments. Routers are central to how traffic flows across a network. Without them, data would remain confined to local segments, unable to reach external systems or remote users. Routers handle all traffic between subnets, making them the linchpins of network design. They act as boundary points between local area networks and wide area networks, between private networks and the internet, and between secure and public zones. Their ability to interpret Layer 3 addressing and enforce policies allows for effective routing, segmentation, and traffic control. At a basic level, routers operate by reading the destination IP address on incoming packets, comparing that address to their routing table, and forwarding the packet to the next hop based on the best match. This process begins as soon as the packet reaches the router's interface. The router does not care about the MAC address. It focuses on the IP layer. By maintaining an up-to-date routing table and following protocol rules, routers ensure that data finds its intended destination even across complex networks. Router interfaces must be configured with IP addresses to function correctly. Each interface acts as a logical boundary for a subnet, meaning one IP address per interface is required. This configuration maps physical or virtual interfaces to specific networks. For example, a router might have one interface on the 10.0.0.0/24 subnet and another on the 10.0.1.0/24 subnet, routing traffic between them. This per-nebus assignment ensures clean separation and proper forwarding behavior. Static routing involves manually defining paths in the routing table. These routes remain fixed unless explicitly updated by an administrator. Static routes are predictable and simple to configure, making them suitable for small or secure networks with few changes. They are often used in lab environments, point-to-point connections, or when tight control over routing behavior is needed. However, they do not adapt to changes in network topology, which limits their scalability in dynamic environments. A default route, often written as 0.0.0.0/0, acts as a catch-all for traffic destined for networks not explicitly listed in the routing table. This route points to a default gateway, typically the next hop toward the internet or another upstream router. Default routes are common in smaller networks or at edge routers that do not maintain full route tables. They simplify configuration but can introduce risk if not properly controlled, as all unknown traffic is sent in a single direction. Next hop decisions are a core part of how routers function. When examining the routing table, routers use the longest prefix match to determine the most specific applicable route. This means a route with a /24 mask takes precedence over a /16, assuming both cover the destination. Once the best route is chosen, the router either forwards the packet out a local interface or sends it to another gateway. The final step before delivery involves resolving the next hop IP address to a MAC address using the address resolution protocol. Packet encapsulation changes at each hop across a routed network. When a router receives a packet, it strips away the old Layer 2 frame and replaces it with a new one appropriate for the next interface. This includes updating the source and destination MAC addresses while preserving the original IP header. The time to live field in the IP header is also decremented by 1. This process prevents packets from circulating endlessly and ensures that routing decisions are made freshly at each device along the path. Routing tables are the central logic point in every router. They include different types of entries: static routes, which are manually added, directly connected routes, which are automatically recognized when an interface is assigned an IP address, and dynamic routes, which are learned through routing protocols. Each entry includes a destination network, subnet mask, next hop address or exit interface, and a metric or administrative distance that influences path selection. Understanding these entries is essential for interpreting routing behavior and troubleshooting connectivity. Routers separate broadcast domains, preventing broadcast traffic from propagating across the entire network. Each interface on a router represents a boundary, isolating broadcast traffic within its assigned subnet. This containment improves network efficiency and limits unnecessary traffic. Without routers, broadcasts would flood all segments, degrading performance and increasing the chance of collision. Broadcast domain separation is one of the primary reasons routers are placed between network segments in any structured network design. Routers also provide traffic control using access control lists. ACLs are rules that filter traffic based on criteria like source and destination IP address, port number, or protocol. These lists are applied to interfaces and operate in a directional manner, either inbound or outbound. The order of rules matters, as packets are evaluated top-down until a match is found. If no match is found, the default action is usually to deny. ACLs provide security, bandwidth management, and policy enforcement, making them a critical feature of router configurations. For more cyber content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. The routing process on a router follows a specific sequence of steps. First, the router receives a packet on one of its interfaces and performs an IP lookup by examining the destination IP address. It then searches its routing table to find the best matching route using the longest prefix match. Once a match is found, the router makes a forwarding decision by identifying the correct exit interface and next hop IP address. The router then resolves that IP to a MAC address using the address resolution protocol and encapsulates the packet with new layer 2 headers before forwarding it. Routers handle both interior and exterior routing responsibilities. Interior routing takes place within a local network or autonomous system and is typically handled by protocols like RIP, OSPF, or EIGRP. Exterior routing connects networks across public boundaries such as the Internet and uses protocols like BGP. Routers on internal LANs often use private IP address ranges and focus on internal path efficiency. Internet-facing routers handle address translation, security policies, and traffic shaping to manage external communication and protect internal resources. Placement of routers within a network design is strategic and intentional. Routers are typically positioned between major subnets, acting as the decision point for traffic moving between departments, data centers, or zones. They are also placed at WAN edge locations to handle internet connectivity and remote site links. In larger networks, redundancy planning is essential, often requiring multiple routers in high availability configurations. Multiple routers in a high availability configuration. These setups use technologies like VRRP or HSRP to ensure that if one router fails, another can take over routing responsibilities instantly. Routers play a central role in network address translation, or NAT, which allows private IP addresses to communicate over public networks. NAT translates internal IP addresses to a single public-facing address, making it appear that all traffic comes from the same source. Port address translation, or PAT, maps individual sessions to specific port numbers, enabling multiple devices to share one public IP. NAT improves security by hiding internal addresses and conserves IP space, both of which are critical for internet-connected networks. The time to live, or TTL, field in a packet's header serves an important function in loop prevention. Each router that forwards the packet decrements the TTL by 1. If the value reaches 0 before reaching its destination, the packet is discarded. This prevents endless circulation of misrouted or undeliverable packets. Hop count, which tracks how many routers a packet passes through, is another important measurement in path selection and troubleshooting. Both TTL and hop count help ensure routing behavior remains efficient and error-free. Diagnostic tools built into routers help troubleshoot connectivity and performance issues. Ping sends ICMP echo requests to test basic reachability, while traceroute maps the path packets take by incrementing the TTL and observing responses from each hop. Route inspection commands show the current routing table, revealing how paths are selected and which networks are reachable. Interface inspection commands display link status, error counters, and protocol behavior. These tools are vital for diagnosing faults, confirming connectivity, and validating configuration. Router hardware capabilities vary depending on model and use case. High-performance routers used in enterprise environments typically include powerful CPUs, ample memory, and multiple high-speed interfaces. They may support fiber connections, modular interface cards, or built-in encryption acceleration. Routers at the branch or home level often have fewer features, but still perform core routing functions effectively. Throughput ratings, measured in packets per second or megabits per second, determine how much traffic a router can handle without degradation. Routers carry the responsibility of moving packets between networks, enforcing routing logic, and enabling communication between different segments. Their ability to make dynamic decisions based on destination addresses and path cost makes them essential for scalable network architectures. They also provide policy enforcement through ACLs, support for NAT, and interface-level configuration that affects how traffic flows. Without routers, networks would be isolated and unable to communicate beyond their local segment. In summary, routers perform IP-driven forwarding, serve as gateways for traffic between different network zones, and apply rules that dictate how data moves across networks. They separate broadcast domains, manage routing tables, and play a critical role in enabling secure and efficient communication across all layers of a modern network. Whether connecting internal subnets or providing access to the internet, routers are at the core of every network's functionality. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.